Giancoli 6869, just more energy stuff. Really just talk about conservation of energy and how energy transforms. There are other forms of energy, electric, nuclear, thermal, chemical. Um, Really, thermal's the main one that we'll be able to quantify. We will at some point, probably these two, but this one's for sure what we're talking about today. Um, but work is done when energy is transferred from one object to another. And now we know that total energy doesn't increase or decrease. As a whole, it's conserved. So there are non-conservative forces such as friction, but where do the kinetic and potential energies go? Well, they don't disappear, right? I mean, heat's conserved, so they become heat. So the actual temperature rise of the materials involved can be calculated, and we can do thermodynamics to do that. But the big thing is we just want to find the work that's forming here. So when we solve these problems, one, we want to draw, as always. We want to find a system for which energy would be conserved. So we want to break it down. We want to figure out what we're looking for and decide on initial and final positions. Where are we starting, where are we finishing? We want to use a reference frame, which is normally us observing. We want to apply conservation of energy, where we have an initial and a final, and then we solve. So here's an example. We got friction on a roller coaster car. So we got a roller coaster car that's up here, all right? And it drops and then comes back up to a height of 25 meters. It traveled a total distance of 400 meters. We want to determine the thermal energy produced and estimate the friction force. Again, it's rough. And then the car's mass with the people in it is 1,000 kilograms. Do it now.
All right, you can see I got my Christmas break beard going here, so get to see a different look. Friction on a roller coaster car. So we have a car and it traveled a total distance of 400 meters. Determine the thermal energy produced and estimate the average frictional force of the car whose mass is 1,000 kilograms. So we start here, we go to here, we go to here. And okay, so it comes to a stop at the top. All right, so we have initial velocity of 0 and a final velocity of 0. So we lose energy when we go from here to here, right? And we want to find out what that energy is. So let's just take a look at this. This is all potential. And this is potential energy final. And we want to find the difference that happens here. So potential energy initial, mg h initial equals mg h final. Or so we would think, right? But there's going to be a little loss there, and that little loss will be our work that's going to happen, okay? So what we have is our mass, and our mass is 1,000 kilograms times g, which is 9.8, times our height of 40 meters. Our mass is still 1,000, our g is 9.8, and our new height is 25 meters. And then there's going to be some work that happens here. So I solve this, subtract this, and that will tell me how much work is going down. So 1,000 times 9.8 times 40 gives me this number minus 1,000 times 9.8 times 25. And I get a difference of, I take this minus that, of 147,000 work. So that's how many joules of thermal energy we have. So that's the energy produced. Now the frictional force in the car, right? So work is force times distance. And since frictional force is really the only force acting, we take force times distance should equal 147,000. It says our distance is 400 meters. So if I divide that by 400, that would give me a relative average frictional force of 147,000 divided by 400. So our frictional force is 367.5 newtons. So So that's the force of friction acting on our car during that entire trip. And again, that's average, not at each individual location.